Okay, good afternoon, everybody. I hope everyone's having a wonderful day. So today I'm going to be talking up and picking up from where I was last day. So last day I introduced you to the recursion tree method. We'd seen a couple of examples last day. We walked through the process of analyzing a recursive algorithm just to see how it gets adapted for the idea of a recursive, for analyzing a recursive algorithm, which we've seen already before this. It's just that I wanted to kind of generalize it a little further so that you can play around with the ideas more generally. Now, I wanted to kind of talk a little bit more about the recursion tree method, just a couple of remarks to build up to the next result I would like to talk about. So, one thing that you should notice from a couple of the examples we did, and there's also other ones in the notes, and all of them sort of have an interesting structure to them, but in different ways. So when you have the recursion tree, it always depends on the recurrence how you analyze it, right? But in the recursion tree method, generally, this is just kind of an intuition for this, is that it seemed like the recursion tree tends to do one of three main things, assuming that all of the sizes of the parts that we subdivide into, you know, when we like half the size or put it in thirds or something like this, or I decrement it by one, I always decrement. But I always decrement where all the recursive calls all decrement by the same amount. So either by dividing by 2 or I subtract by 1. All my recursive calls all have the same size for the input they're going to be applied on. So this doesn't necessarily have to be the case. With the recursion tree method, you can actually have it where you have two separate recursive calls, one where one actually makes a larger chunk than the other part. As I mentioned down here, I mentioned here that you can still use the recursion tree method, but let me draw a little doodle for what I mean by this. So suppose you have, say, a couple of recursive calls, where one of them, so suppose that I have my size for n, so say there's n steps that happen. Now keep in mind, I usually draw these as the notes, but this is just a quick picture, just a doodle off to the side. You may have it where like one of the recursive calls does a quarter of that work, but the other does, say, 3/4 of the work. But notice that this isn't the same size as that. You can still use the recursion tree method as we described it last day, where you draw out and you carry out all that recursion by birthing children for the tree. And yes, I had to describe it that way because it sounds fun. So it creates children every time I do a recursive call, and I draw in the node where I have these circles here, I put how much the non-recursive work is for that given recursive call, which naturally could spawn more children until eventually we get to the leaves, and the leaves correspond to our base case. So it's like I'm walking through a call tree for all the recursive calls. And naturally we figured out, okay, how many levels were there? And we try to find a pattern for how much work is happening non-recursively at each level by summing over it. So we try to find a general pattern for this. So you could still do the same thing, but notice that if they're not the same size, it may be the case that one of these sides may be taller actually than the other side. So one actually might grow a little slower than the other one. Naturally, one way you can adapt the recursion tree method to adapt for this is you just figure out which subtree actually grows, it reaches the base case slower. So notice here that in this case here, it divides by 4 every time. Versus this, where it's just 3/4 of it every single time as I go down. Which one will reach the base case first? The one where I quarter it, or the one where I take 3/4 of it? So I must stress that when you do this recursive call, you'll have one here where it's a quarter of whatever this is, a 3/4 of this other one. So would it be the left one or the right one that reaches the base case later? If you think about the branches. So think about it, just think about it. Yeah, the right one would take longer probably, right? Because it's 3/4. So every time I make it smaller, it's always 3/4 of the original size versus the other side, which is a quarter of the size, which is much smaller, right? So that means that all you have to do when you adapt the recursion tree method is you just figure out what the longest possible pathway down to the leaf is, and you take this as the number of levels. That's all you have to do. So you just take that as the number of levels. You do the exact same process we just described, except one thing I'll stress is that if you use this approach, you might only end up with a big O result as opposed to a big theta result. This is because we're being a little loosey-goosey, because one of these trees actually might be much shorter than the other one. One example of this would be if you're computing, say, the running time of the recursive version of Fibonacci. If you've ever seen the example of computing the nth Fibonacci number using recursion, if you use a recursion tree method, the technique I just described here works to prove that the running time is big O of 2 to the power of n, but there's actually a much tighter result which requires a little bit more analysis that's based on the golden ratio. But yeah, so that's just a remark I want to make. But the point here is that there's generally, when we have them of equal sizes, they fall into one of these three groups here. So notice here, these aren't the same size for my recursive calls. So notice that as we go down the tree, it may be the case that the work is actually decreasing. So if I look at the amount of work happening at each level, it's just going down as I'm doing this. So if this happens, that means that the work, or the number of operations, if you think about it as an algorithm, and this is representing its complexity function, you think about it as the amount of work happening is being dominated at the initial call of the algorithm. So this first case is that. The second one is where the work is roughly equal at each level of the tree. But all that means is if you know the height of the tree, if you want to figure out the total number of operations, remember we sum over all the levels, right? If the number of levels is always one more than the height. So if you want to figure out what's happening is roughly the height times the amount of work per level. So that's the second case. So I do have an example in the notes with this. And in fact, we're going to see an example that's quite similar to this today. The third case, this is when simply as we go down the tree, there's a lot of recursive calls, many of them. That means that at the end of the day, as we go down, what happens is the work increases as we go down the tree. So when I'm talking about this, I mean that the work itself is going down. But the thing is that the number of leaves is going up. So this will be a the technical term is it'll be a very bushy tree at the bottom. So it'll be a very bushy tree, has lots and lots of recursive calls. This is when the recursion overtakes all the non-recursive work that happens if otherwise I was dealing with a larger input like at the beginning of the algorithm. So naturally it falls into these three cases when you actually draw out the recursion tree in the case when all of the sizes of our recursive calls are of equal size. So I'm hoping that you get a general intuition for this. If you take a look at the examples I have for the recursion tree in the notes, I give a couple of other examples there. You'll see that each one of them roughly falls into one of these. So naturally, these are three cases, and when I have three cases, you could actually sit down and formally prove this, but you actually end up with three cases that correspond to a very nice cookbook approach to coming up with tight asymptotic results for specific forms of recurrence relations. And this brings me to talking about the so-called simple master theorem. So let's head over here and let's talk about the simple master theorem. So this is a term that I use because there's several different master theorems, and it even depends on which book you pick up. For example, different books have different names for their master theorem. So this is the one I'm giving you as the simple master theorem. There's a different master theorem that is actually presented in the notes I'm going to ask you to read, which is actually a generalization of this one, which handles even more recurrence relations. So I must stress that even with the recursion tree method, you can handle more recurrence relations than these theorems are capable of. But I must stress that if they have a very specific form, I actually have a very simple way of evaluating their asymptotic behavior in terms of big theta, which is very nice. So you can almost look at this like a cookbook way of handling any kind of recursion that you want to play around with. So if you have a recursive algorithm, if it fits the form of this theorem, then you could just apply it, just flat out. So you just tell me what constants you use for the theorem, and then you just invoke it. It's really nice and simple in that way. So it's much less work for us rather than having to draw out the recursion tree like this, or potentially using substitutions or other analytical techniques. So hopefully for you, you're like, oh man, that's wonderful. I have a much simpler way of dealing with determining the time complexity of recursive algorithms. This is a much, much simpler way of approaching this. So I must stress that if you ever wanted to sit down and actually prove this theorem, it actually falls into the 3 cases I have here. And naturally, those 3 cases are the 3 cases I have in the theorem. So if you're wondering about that, that's actually where they come from. So anyways, so you can think about this. Rather than having to look at everything carefully, you could just simply apply this theorem if it fits the form of the recurrence relation. So you got to remember when it's applicable to apply this theorem and when it's not. I must stress that the much more general Master Theorem that's in the notes, this is the same one that you'll find in one of the recommended books, Introduction to Algorithms. It's in CLORS, CLRS. The Master Theorem, there is the Master Theorem that's in the notes, if you're curious about that, if you find yourself having access to that book. I do have a few examples, by the way, which I'll mention in a moment. But the point is, let's talk about this so-called simple Master Theorem. And some people call this actually the Master Theorem too, just to be very clear. There's all sorts of people talk about Master Theorems and they may not necessarily be the same one. The point is it's called the Master Theorem because you can think of it as the master that tells you which, it's like the ultimate go-to for analyzing recursive algorithms. That's why it's called the Master Theorem. Just like you have a master lock, so you can have like a key, you put the master, like it's the same idea. So anyways, so suppose I have constants, and I must stress that there's plenty of constants in this theorem. So let there be constants a, b, and s, which are all going to be integers, and I'm going to have c, d, and k, which are real numbers. And they're going to be as follows. Now I must stress, it's very important to know the domains of these numbers. So if they do not fall into this, they may not necessarily be applicable to the Master Theorem. Well, the simple Master Theorem, to be a bit more precise. To make this simpler for myself, I'm just going to abbreviate simple Master Theorem as SMT like this. Just because writing out simple Master Theorem every single time gets kind of boring after a while. So anyways, so we have these constants, so a is greater or equal to 1, b is greater or equal to 2, c is greater than 0, d is greater or equal to 0, k is greater or equal to 0, and it has to be in this specific theorem that n and s are a power of b. Do you recognize this form, by the way? Do you remember me talking about things in terms of a power of b? Do you remember me talking about this idea before? There was some place where I talked about this in a lecture. It was very recent, and it started with an S. Do you remember there was this thing that I brought up? There was an interesting theorem that I told you it's very handy. It's very handy, and it sort of seemed to come out of this magical ether that was beautiful from an analytical standpoint because it made it allow us to make a lot more assumptions and we could still get the same results. So if I'm spreading butter on a piece of paper, not a piece of paper, I don't want to eat the paper, by the way, on a piece of bread, if I spread it on, I want to spread it what way? I want to spread it smooth. I want to spread it smooth. So do you remember I talked about the smoothness rule before, right? So there's actually caked into this theorem is actually the smoothness rule. Just I don't write it out. So just if you're looking at this and you say S is a power of A and N and S are a power of B, it's just from that assumption. So think of it more like a cog as a part of the analysis. So you can make this as a simplifying assumption in your analysis. Just be aware of that. So I'm going to suppose I have a recurrence relation T with input N, and it has to be that it's eventually non-decreasing. That's a very important stipulation. Otherwise, it's going to have it where the function can suddenly start growing and growing and growing, and that's going to be a problem for us. We need to make sure that there's a certain value of N that will allow it to behave like a non-decreasing function. So anyways, here's the form. So I have T of N is equal to A times T of N over B plus Cn to the power of k, if n is greater than s, where T of s is equal to d. So you might look at this and say, Dan, that seems rather specialized. And the answer is actually, believe it or not, it's actually quite broad. So remember, all these constants, they can take on all of these possible values. So I could just pick those constants, and if they fit this form, we're okay as long as the t is, in fact, eventually non-decreasing. And if I have it in this form, under these conditions, I can say the following about t of n. So this is something you get from the theorem, and it's unconditional. Notice that n and s are power b in the conditions of this theorem, but it is not required for the conclusion, just to be very clear. This should remind you of the smoothness rule. So, I have t of n is big theta of n to the k if a is less than b to the k. So this is actually case 1. That's case 1 that I just mentioned over here. This is when that non-recursive work at the root or at the top of the tree in our recursion tree is dominating all of the operations over all of them when I sum them up. So that's what case 1 is. So this is actually just case 1, which is rather intuitive if you think about it. If the non-recursive work is c times n to the k, if that's what's dominating the running time at the root, most certainly all the other stuff that happens is going to be less dominant than this when I sum over all of them. That's the intuition I'm trying to give you here. Second case, this is when I have it when the amount of non-recursive work happening at each level of my tree is equal at every single one of the levels. So roughly equal. So think of it as the amount of non-recursive work times the height of the height of the recursion tree. So that means that in the second case, it's t is big theta of n to the power k times log base b of n. So hopefully these intuitions are helping you understand why these two cases are what they are. So this is when a is equal to b to the power k. Finally, this is when the leaves of the tree dominate the running time. So if you ever want to determine the number of leaves in a tree with a given height, well, simply it's n to the power of whatever that height is. But this is one equivalent way of writing that out if you use the definition of the logarithm carefully. You end up with big theta of n to the power of log base b of a if a is greater than b to the power k. So this is case 3. So the 3 cases I gave there, they correspond to these 3 cases. So hopefully they help you remember what these 3 cases are, because I'll expect you to know these 3 cases. So one thing I want to make a remark about with this theorem is that the cn to the power of k can simply be replaced with big theta of n to the power of k. So note that this term right here has to be of a form of some polynomial. That's one constraint that this theorem has. So just be very wary of that. So are there any questions about the statement of this theorem before we do some examples? You're going to see that it's really nice, as it is going to, you know how we drew out the tree and we did all that work, and you've seen how I did the iterative substitution, we've seen that work that I did, even those simplest cases. Now some of those will not be applicable to the simple master theorem, such as our first example we did last day, but the last example most certainly could. But I want to do some examples with this. Are there any questions before we proceed? Because you're going to see that it's really nice. This looks like it has a lot of stipulations, but as long as you remember the conditions of these constants and what t of n has to look like, it's really just like this. Just a snap of a fingers, like 2 sentences, boom, you got it. So it's like one of your best friends. So if you find yourself in a predicament where you're like, hey, look, I need to determine the running time of my recursive algorithm. Does it fit the form of the simple master theorem? And I call it the simple master theorem because it's simple to apply and it applies to simpler recurrence relations. This is in contrast to the master theorem, which has more conditions to it requiring you to do more work to meet one of the 3 cases, which the 3 cases there in the master theorem, they correspond to the same 3 that I gave here, just they apply to a broader class of recurrence relations, where, for example, you'll notice that I have cn to the power of k over there for the non-recursive work. You can actually just have a function right there with some very tight restrictions on that. So that being said, let's do some examples. I'm hoping that you'll see this and be like, yeah, that's actually kind of nice. So let's do an example. So let's consider when t of n is equal to t of n over 2 plus 1, where t of 1 is equal to 1 and n is a power of 2. So one thing I'll make a remark about this is that actually if you take the running time of binary search, for example, and you do the same technique we did last class, believe it or not, if you formulate the recurrence relation, it'll look just like this one. So if you're wondering, how would I do something like with binary search? It would actually look just like this one if you assumed n was a power of 2. So I'm actually secretly showing you a bunch of different ways of applying these things to algorithms you're aware of. So let's try applying the simple master theorem. First, we need to see if it's applicable. So we got to figure out if, so let me just write, we apply the simple master theorem. Where, now remember, like I said, we have to know if it fits the form. Now, we can see quite clearly that n and s are powers of 2, right? So s in this case was just a 1, right? That's not really interesting for us. And n is indeed a power of 2. Remember, these could be simplifying assumptions your analysis makes to come up with this recurrence relation. So just remember that. It's a tool that is very helpful. So you don't have to do all that extra work. It's something that saves you a little bit of time. So can somebody tell me what's A here? What's A? So what would A be? Let's see. Well, while you're thinking about A, I'll tell you what B is. So B is 2, right? So far we know B is 2 because you'll notice that 2's right there. That's what B is. Yeah, it's just 1, exactly. Perfect, perfect. So naturally, you can see I have 1 here. So I'm just going to make C is equal to 1. I'll make K is equal to 0 because you know that n to the power of 0 is just equal to 1, right? And the other one that's of interest for us is D. Notice that D here is just 1. So now I have identified the constants. Now all I have to do is determine what happens with A and B to the power of K. So notice that A is equal to B to the power of K as 1 is equal to 2 to the power of 0, right? Remember, B is 2, K is 0. So A is 1, so that means that they're equal, right? So A is equal to B to the power of K as 1 is equal to 2 to the power of 0. So we have case 2. This says that the following. It's that I'm just going to plug in what the second case is, and then I'm going to simplify. This says T is big theta of n to the power of 0 times log base 2 of n. Right? Therefore, T is big theta of, well, n to the power of 0 is just 1, right? So that means that T is big theta of log base 2 of n, which you know about because binary search has a logarithmic running time, right? So it's really just that simple. So no funny trees, no analytical techniques I'm pulling out here. It's really simple. It's just remembering all those constants and the form of the recurrence. So are there any questions about this example before we proceed to another example? So remember, the game plan here is very simple. Figure out the constants, assuming that the form fits, because these constants will always exist if it fits the form. But although, make sure, of course, that it has the form, right? I can always give you recurrence relations that don't look like this at all. But the thing is, they have to fit the form. So if we're okay with, actually give me 2 thumbs up if we're all good so far. I just want to make sure. Okay, wonderful, wonderful. Okay, good, I'm seeing lots and lots of thumbs. Wonderful. That's what makes my Tuesday. So let's do another example. So let's consider where t of n is equal to 3t of n over 4 plus 3n squared, where t of 16 is equal to 1, and n is a power of 4. So all we have to do, so first I will tell you up front that that does fit the form. If you could check, for example, the conditions around n and s if you'd like, but it looks like it is the case because s here is a power of 4. It's 4 squared, right? So one thing I'll mention, of course, this is for when n is greater than 16, just to be very clear. But anyways, so let's try applying the simple master theorem. So I'm going to identify the constants. Can somebody tell me what A is? What's A? So what's A here? It's 3. Very good, very good. How about B? So what's B? 4, right? Very good, very good. Okay, and now next we have C. And we have C, K, and D. So we got to figure out what C, K, and D are. What are C, K, and D? So I'll tell you up front that K is 2, right? Because it's n squared. Yeah, C is 3, very good, very good. And then we had K is 2, and D is what? What's D? This one's an easy one. I know you guys got this. It's a piece of cake. It's a piece of cake. Don't make it look like it's a lot complicated than it actually is. It's very simple. It's the simple master theorem. It's just 1. It's just 1. It's the amount of non-recursive work that happens in the base case. So, which is the amount of operations that occur in the base case. In this case, it's just 1. So that's when t of 16 is equal to 1. So it's just when d is equal to 1. So, and I'm going to change that period into a comma because it's fun. And a is less than b to the power k as 3. So b is 4 and k is 2, right? So we know right away that 3 is less than 4 squared, right? Because 4 squared is 16. What the variables mean? These are the exact ones that are in the theorem. So let's just pull this out. So this right here, this is what A is. This right here is what B is. This is C. This right here is K. And this is D right here. I should have used a different marker for that one. But see, all I'm doing is identifying the constants. It's all I have to do. It's like using a cookbook. Just I just follow the steps of the conditions. Now, just like baking a cake, it doesn't have to be that simple, though. Most certainly, you have to know it fits the form of the recurrence, though. If it fails to for the simple master theorem, you may not be able to apply it. But yeah, so if we know these constants, let's figure out what case it is. So we have case 1, right? That's when A is less than b to the power k. And by the simple master theorem. So notice I'm invoking it. I have to make sure I invoke this at some point. And by the simple master theorem, we can say that t is big theta of n squared. So are there any questions about, any other questions about the second example? Don't be shy. I'm very happy to answer any questions. Because we'll do one more example. Okay, so if we're okay, let's proceed to do a third example. I'm going to move over here. Just going to boogie on over this way. So I'm just going to kind of move on over here. And let's do our third example over here. Seeing as I have the simple master theorem just sitting right here. So just as a reminder, remember, this is the form you're looking for, where we have a times t of n over b plus cn to the k. So notice that every example we did last day actually doesn't fit this form. Like I said, the first example we did didn't. It's because I decrements by 1 every time. It doesn't subdivide. You're going to run into a lot, when you run into a lot of so-called divide and conquer algorithms, which we're going to talk about very shortly, they follow very similarly into this form. So a lot of the recursive algorithms you've seen, including many sorting algorithms, such as your merge sort and quick sorts, normally their running times look like this. So a lot of so-called divide and conquer algorithms have forms that look like this one. So we'll talk about that actually just after this example. So essentially I'm going to be giving you just a wide way of applying this technique to all sorts of different algorithms, which is really nice. It's nice. It's nice. So let's do a third example. So let's consider when we have t is 9 times t of n over 3 plus n, where t of 3 is equal to 3, and n is a power of 3. So one thing I'll tell you up front, if you haven't started working on the assignment yet, if you haven't taken a peek, you'll get to play around with this simple master theorem. My expectation is that you'll be able to apply these cases. So I'll expect you to know the cases and have the ability to apply them. As long as you remember the intuition behind these 3 cases and remember what this form looks like, it's a piece of cake. It looks like a lot, but it's really not. It makes things actually quite nice and very easy to apply. So now that I have the form actually just down here, it makes things actually a little easier here for if anybody isn't taking note of this. So let's figure out what the constants are. We see that, let's figure out them all together. So we're going to get A, we have B, we have C, we have K, and we have D. So tell me what A, B, C, K, and D are. So far we got A is 9. That is correct. What else do we got? So far we got A on the table. We got A on the table. We need B, C, K, and D, everybody. We got B is 3. So far we got a B is 3. That's correct. I'm loving this. I feel like a game show host. So let's see. We got D is 3. We got B and D. Let's see. Yeah, B and D are 3. Very good. Very good. So far we got D sorted out. We got D sorted out. We have C and K to deal with. What are C and K? 1 and... Now, so far we got... So we know right away it's just an N here, right? So remember the form. It's Cn to the K. So if I make this 1, it's just going to be N to the K. But what's K here? It's 1. Very good, very good, very good. It's just 1. That's it. And boom, there you go. That's all you have to do. So we see that A is 9, B is 3, C is 1, K is 1, and D is 3. And we have to determine what is happening with A and B to the power K. So let's look at our 3 cases here. So let's see. So depending on A and B, so remember A is 9, B is 3. So we have to determine, is A less than B to the power K? Is A equal to B to the power K? Or is it that A is greater than B to the power K? Which of the 3 cases is it? Let's see, we got 1 for less than. We got 1 for greater than. So far we got 1 for less, 1 for greater than. Well, let me proceed here. So let's see. So remember, A here is 9. Remember, A is 9, and we have B is 3, and K is just 1, right? So it means that this is just 3 to the power 1. So 9 has to be bigger than 3 to the power 1. So we know right away if we have this, it's okay, it's okay. So we know that because A is greater than B to the power K, we're going to apply case 3. So do you see the intuition behind this? Is in one of the cases, what's happening here, the non-recursive work is fairly big, but there's very few recursive calls happening. If there's lots of recursive calls, but not so much work happening here, you might get the 3rd case. And when they're about even, if you take a look at the recursion tree, you end up with case 2. So we have case 3. Then I'm just gonna spell out what it says right here. Then T is big theta of n to the power of log base B of A, but B is 3 here, and A is 9. And I'm just gonna put my conclusion in. So can somebody tell me what log base 3 of 9 is? What's log base 3 of 9? So think about it from the definition of a logarithm. 3 to the something is equal to 9. What is the something? It's 2. It's 2. Very nice. So therefore, I'm just going to apply the simple master theorem. So I say by the simple master theorem, T is big theta of n squared. Isn't that nice? So it's really nice and simple. Hence why I call it the simple master theorem. It covers a wide class of recurrence relations, and it's very simple to apply. So just a couple of remarks I want to make, just before I get too ahead of myself, is that I wanted to note about this thing that I mentioned when I gave you the simple master theorem. Notice that I said that you can replace the Cn to the power of k with big theta of n to the power of k. This is because of the way this form is. This form is big theta of n to the power of k. So if you ever find yourself wanting to formulate a recurrence relation, you don't actually have to identify C. So if you choose to write out what C is, I encourage you to do it. But if instead you're just doing analysis, you can easily replace the non-recursive part with big theta of n to the power of k. So you can literally write that in. And you can still apply the simple master theorem, you just won't have a C. It'll just mean that there exists some C. And that's all it means. So just be mindful of that. One other detail I want to warn you about is, remember I talked about this form business. So I want you to warn you, so I'm just going to say, so be careful about the form for the simple master theorem. So this is applicable just as much to things like the master theorem, is that you have to be very mindful of the conditions of the theorem. So for example, if I give you a recurrence that looks like this, T of n is equal to the power of n times T of n over 2 floor of n over 2 plus 1 if n is greater than 1, and t of 1 is equal to 2, where n is a power of 2. So suppose I have this recurrence. So I have a question for you. Does this fit the form of the simple Master Theorem? So the answer is yes or no. It will fall into a definitive camp of yes or no. So just remember what the conditions of the theorem are. So t of n is equal to 2 to the power of n times t of n over 2 with the floor plus 1 if n is greater than 1, and t of 1 is equal to 2, and n is assumed to be a power of 2. So remember what the form looks like. So remember let me use a different marker because I told you I should have used a different colored marker to indicate this. So if I plop in what exactly I would do, there's kind of 3 bits here, right? Actually, there's technically 4. There's D over there. So I have A, this is B, C and K get determined over here, and I have D over here. Are there any issues at all with this? So yes, so that's the main observation you should take a look at. Notice it says 2 to the power of n. Now, is this a constant? That's the first thing. Is it a constant? So notice 2 to the power of n is not a constant. No, we can't use the simple Master Theorem here. This is actually now something that relates to n. So that is not a constant. So we cannot use the simple Master Theorem for this recurrence. In fact, one thing I'll mention is you couldn't even use this for the Master Theorem, which is going to be in the notes for you to take a look at. So you couldn't even use it there either. But one thing I want to warn you about is suppose that this was a valid A. Suppose this was an A. Like this is actually an A. So for example, like it was like 2. Like instead of it being 2 to the power of n, it's just like 2. If suppose that was a 2 instead, could I use the simple Master Theorem here? So sometimes you have to trim off some fat in the description of the recurrence. So look at it very carefully and see if we're still okay. And in this case, let's see. So I get 1 yes, 1 no. So one thing that indeed has been pointed out is there's this issue with this floor sign. But one thing I should note here is that you know that n is a power of 2, right? So if n is a power of 2, if ever I divide by 2, it's always going to be cleanly dividing it. So it's never going to, this floor sign is actually redundant. So one thing I want you to take note of is that in this case, the reason I could not apply the simple Master Theorem is because of what I identified here as our potential A. It's not actually the floor sign over here. The floor sign's okay. In fact, when I make the assumption that n is a power of 2, it doesn't matter that n over 2 is a floor sign. So just be very careful when you look at different recurrence relations. Because, like I said, sometimes there's just a little bit of fat in the description of the recurrence relation, and it really is just something redundant. And this is actually one of the main reasons why things like smoothness are thought about, is that if I think of n as a power of 2, I don't have to worry about rounding up and down numbers. That's one thing that makes things much easier for me to play around with things. So that's one of those analytical tricks I'm just encouraging you to think about. So if you ever see it in the future, it's to save you time. So anyways, are there any questions about the simple Master Theorem at all? Don't be shy. So a question. So if it weren't a power of 2, would the floor thing be an issue at all? So remember, in the conditions of the simple Master Theorem, I require that n is a power of b. So if I got rid of this condition right here, I couldn't use the simple Master Theorem because that's a condition in the theorem. So that's one thing. I will tell you that actually the Master Theorem does not actually have a stipulation like this one. Baked inside of it is actually the smoothness, but it's like straight up. Like, the proof is a lot more complicated. If you're ever curious about it, I think the book, the one I mentioned, Course, that's one of the books I have in the course outline. It actually has the proof for the Master Theorem in it, if you're curious about that. I can't remember what page it's on, but it is in there. It's a little bit more complicated, but it is possible to prove it. But yeah, so with the Master Theorem, the full-blown Master Theorem, you don't have this assumption. In fact, you can get away with a lot wider classes of functions that represent the non-recursive work. For example, things like n factorial, you can get away with for the non-recursive work. But there's very strict conditions on it, and it's based on the same relationship we observed at the beginning of lecture. But yeah, no, if there are any other questions about that, I'm going to ask you to take a look in the notes. So I want you to read the section on Master Theorem. So if you understand these three cases, it'll be very natural to see what I mean about how they appear in the Master Theorem. The Master Theorem has stipulations that are based on proving sorry, I'm getting very excited. You know when I say that, you know something's coming that's interesting. So in the stipulations of the Master Theorem, it has it where you're either proving a big omega claim, a big O claim, or a big theta claim. So these big O, omega, and theta correspond to three cases, just like in the cases that I had before here. And yes, it is definitely not a simple Master Theorem. It has conditions to it. So it actually involves proving a claim involving big theta, big omega, or big O. And in one specific case, the so-called case 1, it has a regularity condition, which its proof is very similar to proving a big O claim. Just the constant's a little different. But yeah, so I do have full examples of these. I want you to take a look at that. I'm going to ask you on the exam a very simple question on a multiple choice question about it, just to give you a heads up. But it'll just be there. I'm not going to ask you to do anything more with it. The simple Master Theorem is going to be your friend for the exam. But anyways, I like to make sure you know my expectations up front. But yeah, so anyways, so take a look at that. You'll find that once you see the simple Master Theorem and you understand that one, the Master Theorem is it's arguably even nicer, but at the same time, it comes with the drawback of more conditions you have to prove, which is more work. But as long as you understand the three patterns, those three cases, it's actually still fairly intuitive to know which case to apply. So, but yes, you're absolutely correct. It is not a simple matter. So just remember, look at the big picture of the three cases, and I'll give you an idea of which one to approach with. So, anyways, that being said, I want to move on to talking about divide and conquer algorithms. So the remainder of this lecture we'll probably spend talking about divide and conquer algorithms. If we get a little bit further, we might start talking about dynamic programming, but we'll see. Dynamic programming, I'm very excited to talk to you about. It's one of those algorithmic techniques that at one point you may have thought of as, oh, that's kind of obvious, but at the same time it's also really clever. So, anyways, let's talk about divide and conquer algorithms. So, this is the next main algorithm design technique that I want to talk to you about, and I don't actually have a whole lot to say about it. I just want to show you the structure of one of these algorithms, because believe it or not, you've actually seen several examples of divide and conquer algorithms already. Just, it hasn't been probably given that name, or if you've seen this name, you've never been given kind of like the framework for how you can easily analyze them. So, anyways, actually, just to make this easier for myself, actually, I'll just write it here. Divide and conquer, which I'll just abbreviate as D and C, because divide and conquer every time, it takes a little while to write down. Divide and conquer is an algorithm design technique that expresses the solution that expresses the solution to a given problem, in terms of solutions of similar but smaller subproblems. But smaller subproblems that can be solved independently. So that's very important that they can be solved independently. So just in plain language, there's kind of two parts to a divide and conquer algorithm, the divide phase and the conquer phase. The whole idea is that we take our problem, we break the problem down into smaller subproblems. And we're eventually going to have it reach a point where we can solve a small enough problem where if I can get it down small enough, I could solve all of them and I can combine them together to get the answer. And that's the idea. And there's many ways this could manifest itself as an algorithm design technique. So just the plain language, the algorithm breaks the problem. When I talk about the problem instance when I mean this. The problem into smaller subproblems. Solves the subproblems. And then puts them together. To solve the original problem. So the original instance. So believe it or not, you've actually seen several examples of these actually in previous courses. In fact, we've talked about some of them already, believe it or not. So just a few things. So I'll say you have seen several examples. For example, I know I have to really just load in that example. Merge sort. Merge sort's a classic divide and conquer algorithm. Merge sort, binary search, and quicksort are all good examples of divide and conquer algorithms. So, for example, in merge sort, the whole idea is that you take the problem, in this case you have your input array that you want to sort, you subdivide it into roughly two halves, and you keep doing this down all the way down until you end up with a subarray of length 1 or 0, right? And by definition, each one of those is sorted. And then what it does is it takes those subproblems and it applies, you might recall this from merge sort, it has a subroutine called merge. And what it does is it sorts those two partially sorted arrays, and it passes this back up. So this is this divide phase that recursively breaks the whole problem down, smaller and smaller. And then there's the conquer phase, which what happens is now you have all your smaller subproblems, and you can take each one, you can combine them to solve the overall problem, in this case, sorting the array. Binary search. Binary search is a much more cruder, much simplified example of a divide and conquer algorithm. Here we literally just say, hey, look, I'm just searching for it every time I discard half of the array if I think about it each time. So I take my subarray, I only consider 1/2 each time. So in this case, to solve this is actually a very simple version of this. All I'm doing is I take my problem, I subdivide it by literally discarding half of the elements roughly half of them every time, right? So when I say half, I mean half as per the subarray that I'm looking at. And I keep doing this until either I find it or I don't find it, right? So this is just another but much more crude or simpler version of this idea. And quicksort, I'm sure we talked about this before. You select the pivot, And then the pivot through so-called partition, you'll split into the two smaller subarrays, and you'll have these as in two buckets, and you apply quicksort to each one recursively. And what happens is each one of these recursive calls will divide them down based on the pivot selections until we get down to the point where now we have our subarrays of length 1 or 0. Those will all be sorted by definition. And then we just combine it all together, the so-called conquer phase. So are there any questions about the concept of a divide and conquer algorithm? You've seen actually this idea many times. So it's not like it's something alien. It's very intuitive. So as you're thinking about anything, I just want to note that divide and conquer algorithms are very natural to describe recursively. So I'll just say are described recursively, but this is just me saying, yeah, you can just describe them nicely in this way. Are described recursively. Are described recursively. So this is to make them easier to understand. So I must stress that in practice, you can always transform one of these recursive algorithms, if you're clever enough, into an iterative version. But to make them easier to understand is important for us is because we want to know the algorithm is correct and how long it takes to solve the problem, right? So those are kind of two main things we're interested in this course. So I must stress that in practice, just as a remark about this, in practice, usually one removes the recursion to optimize the algorithm. So this is more of a practical statement than one that's theoretical or fundamental to the algorithm. So I just want to acknowledge that this is a thing. Just be very clear. So I want to give you the general template for a divide and conquer algorithm. Any divide and conquer algorithm that we've talked about, all these ones over here, for example, they all actually fit into this template. So as long as you can see that it fits this template, it's going to be your best friend for the simple master theorem, or just the master theorem more broadly. So let's head over here. I want to describe a general template. And once you see this pattern, it's very hard to unsee it. So let's talk about this form. So if my description over there wasn't clear enough, here's just the idea. So suppose I have a function, and I'll just call it divide and conquer, and suppose that there is an instance called x. So this is our input. So if x is sufficiently small, or simple, then solve it directly. Solve it directly and return a solution. So that's the first kind of big piece of this. So for you, when you've studied recursive algorithms before, what normally is this in a recursive algorithm? Is the recursive case or the base case? So I must stress I wrote it like this to be as easy and adaptable as possible. Or at least as ideally adaptable as possible. So this seems to describe the base case, right? So when you think about a recursive algorithm, effectively, when you think about the base case, this is what you're thinking of, right? Now, in practice, sometimes when you have complicated algorithms that you're working with, in fact, this happens sometimes in practice, actually quite happens often, if they adapt a divide and conquer approach, if the problem gets small enough, what you do is you call another algorithm to finish up and finish off the job. This happens very often with sorting algorithms, for example, in some libraries, where, for example, it might do merge sort at first or quick sort, and then when it gets small enough, and usually it's quick sort, when the instance gets small enough to solve, it might use more of like something like insertion sort or one of the simple bubbling-like sorting algorithms. The very basic comparison-based sorting algorithms perform quite well on small instances. So that's what I'm saying is you could do that right here. So that's the first step. So obviously if it's small enough, just solve it directly. Otherwise, you're going to decompose x. You're going to decompose x into smaller instances. Smaller instances, x1, x2, all the way up to xk. So there's going to be some process for which I determine these. It may be implicit or explicit. So sometimes the loop, for example, will do the job of decomposing them, whether it be through indexing in an array or something like that. But it generally boils down to something like this. For I is equal to, so it's I assign I to be 1 at first, and I go to k. I'm going to do the following. I'm just going to take each one of my xi's, I'm going to apply it to the divide and conquer algorithm. I end up with a solution to that subproblem, yi. Then all I do is I combine the yi's somehow. So I must stress that you don't actually have to combine solutions. If you only have one solution, for example, like in binary search, for example, you only just have one, right? It's not very interesting. So combine the yi's somehow. So like I said, I'm trying to be very broad here. Somehow to obtain a solution y for x. And then you just simply return y. So a lot of the algorithms you've seen before that are divide and conquer algorithms, like the ones I talked about here, they all fit into this form. Many divide and conquer algorithms, they'll just fit nicely into this. So there's other examples of divide and conquer algorithms that do exist. For example, one classic that I don't have time to talk about here, but if you find yourself curious about it, I encourage you to explore it if you know anything about linear algebra, is Strawson matrix multiplication is another classic example. So-called matrix multiplication, using divide and conquer, you can actually speed up the classic or naive matrix multiplication algorithm by a little bit. But I don't really necessarily know how much linear algebra everybody's got here, so I can't go into that too detailed here. But I just feel like mentioning that. There's a lot of examples of divide and conquer algorithms out there, and they all fit this form. It's a general pattern for solving problems. So you might ask, where are all these pieces? Like, where are all this going to go? So anyways, I'm going to tell you about what the constants that I had before. So I'm going to tell you that such an algorithm will have time complexity. T of n is equal to a times b, so a times t of n over b plus f of n, where you can think of a as the number of pieces x is split into. That's what A is. N over B is the size of each subproblem. Of x. So that's what their sizes are. And lastly, we have that f of n, sorry, it's a little bit low there, f of n is the number of operations associated with the non-recursive work. So what we've been referring to as the non-recursive work is just f of n. So these are actually just the 3 bits and pieces. And once you see this pattern, it's really hard to unsee it. Does everybody see that? It's like I could kind of like cookie cutter all of those algorithms and fit them into here. So that's one thing that's really nice about the divide and conquer paradigm, is that once you see it, it's very hard to unsee it. So it's a very common way of solving problems recursively, which is why you've seen examples of it already before. So I want to show you an example of me applying what we just talked about in all these bits and pieces and combine them all together. So let's talk, I'm going to spend the last bit of this lecture talking about merge sort, because I promised you I was going to do a worst case analysis of merge sort at some point, right? And this is a while back. Like, I promised you this like months ago. So I'm going to now do it. I'm sort of like an elephant. I just don't seem to forget these things. So let's do an example. Let's try applying what we just talked about here to merge sort. So I'm hoping I can give you some intuition around how we come up with the time complexity here and all of the ideas we've been talking about up to this point, like the recursion tree, for example. So anyways, so let us consider merge sort. Let us consider merge sort. Recall. So I'm just going to remind you of the main steps in merge sort. I'm going to make the presumption that n is a power of 2 for simplicity here. So I'm going to, just as a remark, I'm just going to assume n is a power of 2. So just keep that in the back of your mind, because it makes it easier for me to describe the algorithm to you. It's not quite exactly like this, but the idea is the exact same. It's n is a power of 2. But it's essentially this. So divide the array into 2 halves, each length n over 2, where n is the number of elements you are considering in that array or subarray, if it's a recursive call. Then all you do is you recursively sort each half. Sort each half. Then you just simply merge the 2 halves. The 2 halves together. That's all merge sort does. Any other time where you have it where it's not like they cleanly divide, you take usually the smaller of the half on one side, or you take the larger of the half on the other side. But it generally boils down to this. So hopefully everybody is reminded of merge sort. This is just the idea of merge sort, right? So let's quickly walk through this. I've got enough time to do this. So I'm just going to quickly jot down the pseudocode, and then we'll knock out this with the simple master theorem. So merge sort. I have a, start, and end. I'm not going to give the driver function or driver method what calls this initially, just for the sake of time. So input, output, we know that we're trying to solve the sorting problem. In particular, we're going to be sorting an interval of the array or subarray. from start to end. That's what we're doing here. So first we check if, in fact, n. Now there's several ways you can cast this description. I'll just cast it like this deliberately to fit the form. If start minus end, sorry, n minus start is equal to 1, then we're just going to return. We're just going to return in this case, meaning that we don't have anything to do. So this is the first step, just like I have over there. Then I'm just going to figure out what the rough middle position is. So I have start plus end divided by 2. So this is what happens when n minus start is greater than 1, right? So then all I do is I call merge sort twice. Merge sort A start to mid. And then I call merge sort again. And I do it from mid plus 1. Let me just write that more carefully. It's mid plus 1 to end. And then I just have this merge subroutine. Merge, which takes A, start, mid, and end. The point here is that this merge part, this takes, you can show that this takes big theta of n. If you're curious about that, see 210. You talk about that in 210, except it's big O of n there, because we haven't really talked about big theta at that stage. Anyways, the big point here is that we have how many recursive calls here? How many recursive calls are happening? So we only got a few minutes here. I want to formulate the recurrence relation based on our divide and conquer algorithm. So I'm going to give the formulation here. So if you want to see more of the reasoning here, just take a look at the notes. But how many recursive calls are happening? Is it 1? Is it 2? Is it 5? Is it 10,000? It's 2, right? There's just 2 recursive calls that happen. So you know that when I were to write out what's happening as a recurrence relation, you know right away that the A, the number of recursive calls that's going to happen is going to be 2. Each one of these, if n is a power of 2, it's going to be exactly a half. So I'm going to subdivide this into 2 halves, right? So I have 2 times t of n over 2 plus everything. If I add up all of these, they're going to get subsumed by the big theta n. So I'll leave it as an exercise for you to convince yourself that the amount of non-recursive work is big theta of n. So this is the case where t of 1 is equal to 1. And I want to give you a quick intuition with this. Just because sometimes students have a I remember when I was first learning about a lot of these things, and I needed some intuition to figure out how the analysis and how all this time complexity gets built up over the recursion. And because earlier on I was talking all about how, there's this thing going on where all the recursive calls, when there's many of them, they influence the running time. And I want to show you a visual representation of this. So I thought a perfect way to conclude things is to show you a visual representation of this. So anyways, suppose that I gave you, for example, t of 4 for that recurrence relation. And I have a block of cheese. So this is the block of cheese. So this cheese represents the running time for the algorithm when I use t of 4 for my recurrence relation over there. So I want to show you how this recurrence relation reflects or corresponds to the algorithm I have behind me. So what I'm going to do is I'm going to cut this into pieces based on how the recursion plays out. So the first thing I need to point out to you is that, remember, if I have t of 4, what happens is it first goes through, and eventually we'll have to do this merge process. That's the non-recursive work. And for t of 4, if you look at my recurrence relation, you're going to have something that's like roughly like linear. So what I'm going to do is I'm going to show you what the non-recursive work for t of 4 looks like. So this is what that looks like. So I'm going to set that aside. But 2 recursive calls happen, each on a half. So each one of those halves, that means I'm going to be calling t of 2. So t of 2 is, so I have 2 recursive calls that happen. So if you notice that each time I do this, if you actually measure out how big these chunks are they roughly the same size? So notice that these look rather similar in their size, right? This is that is not a coincidence. Likewise, notice that this is t of 1. These are all my leaves in the recursion tree all together. So I'd have 4 slices of this. So you'll notice that each one of these 3 pieces, these are exactly each level of the recursion tree. So you notice that each one of these, the sum up of their total amount of work, they're equal, right? So which case of the simple master theorem should I be applying? So there's one, it's case 2, exactly, it's case 2. So let's apply the simple master theorem. So let's just apply the simple master theorem and we'll get on out of here, okay? So simple master theorem, so I'm going to assume, like I said, that n is a power of 2. I should mention that right here, n is a power of 2. But by applying the simple master theorem, if you apply out these constants, you wind up with a is equal to 2, b is equal to 2, k is equal to 1. Notice that c is suppressed within the big theta. So if I look at notice that it's b to the k is just 2, right? That means a is equal to b to the k. So then we have case 2 as a is equal to b to the power k. As in 2 is equal to the power 1. And t of n is big theta of n to the k, where k is just 1, so it's just n. So that means it's just going to be t is big theta of n log n. Therefore, you can conclude that the worst case running time of merge sort is big theta n log n. So with that being said, I'm going to stop right here. And when we come back, we're going to start talking about dynamic programming. Now, yeah, so that being said, we're going to stop right here. And one small detail. I'm going to be including in the notes a little section on backtracking and exhaustive search. I would like you to take a look at it just to make sure you understand the big ideas of it. It's called brute force. Brute force and intro to backtracking. It'll give you a much bigger appreciation for what we're going to be doing next class, but I'll include it there. I'm not going to ask you any questions on the exam about it, okay? I just want to make sure you read about it, okay? I want to make sure you're exposed to brute force and intro to backtracking. So, like I said, we'll stop right here. I want to say thank you very much and have yourself a beautiful day. I'll see you later.